Alright, today we're going to talk about section 5.2, which is comparing two proportions. In section 5.1, we talked about two parallel variables, so looking at data sets where there are two variables that are each changing value. When we want to summarize those variables and summarize the differences between the two groups that we've got, we have to look at how to compare two proportions. Okay, so we're going to start out with the simulation-based approach. Section 5.3 is the theory-based approach, with the exception of the first little step here. This should look pretty similar. Alright, so starting out with an example, we're going to say, is swimming with dolphins therapeutic for people who are suffering from depression? So we've got 30 subjects that have all been screened and have mild to moderate depression. These people are randomly assigned to one of two treatment groups. So either they go swimming and snorkeling for an hour every day, or they go swimming and snorkeling for an hour every day and there's dolphins. I'd be kind of mad if I were in the first group myself, but yeah. At the end of 2 weeks, they evaluate whether their depression symptoms have declined. So the observational unit for this study is an individual with mild to moderate depression. This is an experiment because we are randomly assigning treatments to groups, and the treatment here is whether you get to swim with or without dolphins. Our variables, the explanatory variable is our treatment, right? So swim with or without dolphins. Our response variable is yes or no, did the depression symptoms decline? Right? Alright. So, if we look at our null hypothesis in words, what we really want to know, right, is does the treatment work? Okay, so does swimming with dolphins help depression? What that works out to, though, is did the decline in depression symptoms stay the same between the two groups? Okay, so one way to think about this is for each group we have the proportion of people whose depression gets better, and we want to subtract those two proportions, so proportion dolphin, proportion control, subtract the two, and if that number is positive, right, then swimming with dolphins maybe helps depression. Okay, so our null hypothesis in these situations is that the two treatments are equal. Okay, so whether or not someone swims with dolphins is not associated with whether or not their depression symptoms improve. Okay, our alternative hypothesis is swimming with dolphins increases the probability of substantial improvement in depression symptoms. So there is an association. So when we write that out in math, what we see is that we can say pi dolphins minus pi control equals 0, and that's our null. So the two things are equal. If you want, you can move pi control over to the other side and say pi dolphins equals pi control. They mean the same thing. Our alternative hypothesis is that the difference in the two proportions is greater than 0. And what you'll notice here is that the parameter that we're interested in is the difference in the two probabilities. Okay, so pi dolphins minus pi control. That is our parameter. Okay, so with that one difference, we do basically the same thing that we've always done. Okay, so if we look at the data, we've got 2/3 of the dolphin category, that substantially improves, and 1/4 of the control group that substantially improves. We can plot this out using a stacked bar chart. The only difference between the stacked bar chart here and the stacked bar chart in section 5.1 is that I've turned this one on its side so that it fits on the slide. Alright, so down here we've got the dolphin group and the control group, and we can see that 2/3 of the total number of people are in the orange category, and that corresponds to substantial improvement. And we can see that 1/5, 1/5 of the people in the control group also substantially improved. So what this lets us see is that distance, right, between the two groups and between the two proportions, okay, makes it easy to compare that distance and figure out, okay, this maybe doesn't look like it could happen randomly, right? Alright, so our statistic here is the proportion of people who swim with dolphins and whose depression improved. Okay, so that's 0.6667 minus the proportion of people who improved in the control group, so that's 0.2, which means that our statistic is 0.4667. We could explain this by random chance, right? So that's the null hypothesis. This is exactly like what we did in chapter 3. Or we could explain it with swimming with dolphins really helps depression. So to simulate this, under the null hypothesis, dolphin therapy is no more effective than the control, and we have 13 people whose depression improved and 17 whose depression didn't improve. So if we just randomly assign the outcome labels, improve or didn't improve, to the groups, so dolphins or control, we can compute for each one of those tables a simulation statistic, which is the simulated proportion of people who swam with dolphins that improved, and the simulated proportion of people who did not swim with dolphins that also improved. So we can compute that simulation statistic. One way to do this physically is to label index cards with improve and did not improve, to shuffle them, and then to count out 15 cards for dolphin therapy and 15 cards for the control group, and then calculate the proportions, subtract those, and then repeat. So just like with the simulations in chapter 3, we are counting how many of the simulations produce something that is greater than or equal to what we observed in real life. Okay, so we can go into the applet and do the dolphin study, enter our real data, and show shuffle options, and then count samples. Okay, so let's go to the applets. We want the dolphin study applet. Okay, it's got our data already entered. So we would like to show shuffle options, and I'm just going to have it do 100 shuffles. So we can ask it to show us a 95% confidence interval. We can let's see, we can look at the normal distribution and see that this is only slightly skewed, but our sample statistic is 0.467, and thus our p-value is 0, right, for this particular sample. Alright, So we're counting all of the simulations who had a value of greater than what we observed in real life, and we get 0. If we increase our simulations, do another 1,000, we get a p-value that is 0.0173. So basically, by random chance alone, we would expect to see this not that often. Okay? Alright. So these are just screenshots to walk you through doing that. So, just as in Chapter 3, we go through our 3 S's. We look at the simulation. We do a repetition that corresponds to random assignment. So we assign the response outcome to the explanatory variable. Okay. So think about this kind of in reverse. When we're doing the experiment, we assign individuals to treatment groups. Here we are assigning outcomes to treatment groups. Okay. So our statistic is the difference in the conditional proportions, so computed with our contingency table. And the strength of evidence is the proportion of simulation samples with a value as or more extreme than what we saw in the direction of the null hypothesis. So in this case, greater than. Okay. Now, to interpret this, we have strong evidence against the null hypothesis that the difference in the proportion of individuals whose depression improved between the treatment and control groups is due to random chance alone. So that whole sentence is essentially the same thing that you would have said back in Chapter 3, except that now we're interpreting this as the difference in the proportions. Okay, so we're subbing in words for to describe our statistic. Then we continue on and we say we reject the null hypothesis with p equals 0.0010 or something to that effect, and conclude that there is evidence that swimming with dolphins increases the likelihood that individuals will have an improvement in depression symptoms. Okay? So again, the interpretation mostly stays the same. We're just slightly tweaking the wording to account for the fact that we're dealing with a difference in proportions instead of just a proportion. Right? So, and the generic version looks something like this. We either reject or fail to reject the null hypothesis that the difference in the proportion of whatever the response variable is between the level 1 and level 2 of the explanatory variable is, and then something about what your alternative hypothesis is, right? Because, and you give the p-value for strength of evidence, and then we conclude that, and that relates to the context of the problem. Okay, so pretty simple formula, just fill in the blanks. We can also use that simulation to get confidence intervals. So over here you can see that we have a mean, we have a standard deviation. Okay, it won't let me select the text here, but it'll totally let me drag the red line around. Cool. At any rate, that will give us, the standard deviation gives us a way to construct a confidence interval. Okay, so for any confidence interval, we have our sample statistic plus or minus 2 times the standard deviation under the null hypothesis, right? So in this particular case, our sample statistic is 0.467. Our multiplier is 2, like it always is, and our standard deviation is from the simulation, and we can get a simulation-based confidence interval, which we interpret more or less the same way that we've interpreted every confidence interval. So we are 95% confident that the difference in the percent of individuals whose depression improved after swimming with dolphins is between 10% and 83%, higher than the percent of individuals whose depression improved that did not swim with dolphins. Okay, so you'll notice that I interpreted that as a percent instead of a proportion, you can use the proportion interpretation just as easily. Just make sure that the numbers that you're substituting in match. Okay, so if you're using decimals, use proportion. If you're using bigger numbers with percent signs after them, make sure you're interpreting it as a percent. Okay. So as in chapter 3, the question of whether the interval contains 0 is equivalent to a hypothesis test. So if the interval does contain 0, then we know that there's no significant difference between the two groups. So we can't say that the difference is anything other than 0, right? If the interval doesn't contain 0, you can look to see which side of 0 the whole interval is on, and then construct an equivalent alternative hypothesis that corresponds to where that interval is. Okay? So if the interval does not contain the null hypothesis value, whatever that is, usually in this case it's 0, then the hypothesis test would be significant at the alpha equals 0.5 level. Right? So on the test, if you're asked, what can you say about the hypothesis test for this interval that you've constructed? You would say, if my interval contains 0, the hypothesis cannot be rejected. You could also say, I know that the z value is less than 2 in that case. If 0 is not inside your interval, you could say, I know that z is greater than 2. You could also say, I know that we would reject the null hypothesis at the alpha equals 0.5 level. So, in 5.1, we talked a little bit about relative risk. Relative risk is another way to compare two proportions. Basically, instead of subtracting one from the other, you divide one by the other. And we can do the same significance test for relative risk. Now, think really carefully about what a simulation is doing. The simulation is generating a contingency table, right? Every time we shuffle our cards and split them into piles of 15 and 15, we're generating a table. What we do with the information in that table, that's not actually all that relevant, because what we're looking for is data that is as or more extreme than what we observed. And that information is contained in the table. So, if we conduct a significance test for relative risk, we're going to end up with the exact same p-values that we would get if we conducted a significance test for a difference in proportions. All right? Because the underlying simulated data is the same. So, our hypothesis in this case is that there is no difference, which corresponds to the relative risk is 1, right? So there's no difference in how likely something is to happen in group 1 versus group 2. The alternative hypothesis is that the proportion of people who improve in the dolphins group is greater than the proportion of people who improve in the control group, which means that the relative risk is going to be bigger than 1. If you multiply both sides by p hat control, you get the same hypothesis that we had before, right? Alright, so we expect the exact same p-value, the exact same results. We're just going to change our observed relative risk, or our observed statistic to be the observed relative risk. We get the same p-value, we reach the same conclusion. We can evaluate that conclusion and interpret it as we reject the null hypothesis, conclude that there's strong evidence that the relative risk of improvement between those who swim with dolphins and those who did not is greater than 1. Right? So slightly different phrasing of the interpretation there. I think it's actually a little bit easier for me to parse less extra clauses flying around there, but more or less the same idea, and mathematically the same test, right? Okay, so talking just a bit about strength of evidence. If the difference between p hat 1 and p hat 2 increases, then there's stronger evidence that the population proportions differ, right? P1 and P2 are further apart, the difference is bigger, therefore we have stronger evidence. If we have a bigger sample size, we have a smaller standard error, right, which also leads to stronger evidence. So the difference in the proportions is our sample statistic, right? And that is the middle of the confidence interval that we have. So know that the difference between the proportions is the midpoint of the confidence interval. And know that larger sample sizes produce narrower confidence intervals. All right? And that concludes section 5.2.